Designing scalable AI systems. Designing scalable AI systems is a critical component of modern AI system architecture and design principles. As AI systems become more integrated into various industries, ensuring their scalability is paramount for handling increased loads, expanding functionalities, and adapting to new technological advancements. This lesson focuses on actionable insights, practical tools, frameworks, and step-by-step applications to empower professionals to design scalable AI systems effectively. Scalability in AI systems refers to the ability of a system to handle growing amounts of work, or its potential to accommodate growth. An effectively designed scalable system can manage increased data volumes, user demands, and processing needs without compromising performance. One of the foundational frameworks to consider when designing scalable AI systems is the microservices architecture. Unlike monolithic architectures, which bundle all components into a single unit, microservices allow for building systems as a suite of small, independently deployable services. Each service in a microservices architecture can be developed, deployed, and scaled independently, facilitating greater agility and scalability. A practical tool to implement microservices is Docker, which enables containerization. Containers encapsulate a software component along with its dependencies, ensuring consistent behavior across different environments. This consistency is crucial when scaling AI systems across different servers or cloud environments. Kubernetes, an open-source platform for managing containerized workloads, is another vital tool that automates the deployment, scaling, and management of applications. Together, Docker and Kubernetes provide a robust infrastructure for developing and scaling microservices-based AI systems. Another critical aspect of designing scalable AI systems is efficient data management. AI systems thrive on data, and as they scale, the volume of data they process increases exponentially. Apache Kafka, a distributed event streaming platform, is instrumental in handling real-time data feeds efficiently. Kafka's ability to process millions of events per second makes it an excellent choice for scalable AI systems that require real-time data processing and analytics. Additionally, Apache Spark offers a unified analytics engine for large-scale data processing, supporting various programming languages and providing high-level APIs. Spark's in-memory processing capabilities significantly enhance performance and scalability, particularly in AI applications that require iterative computations. Machine learning models are at the core of AI systems, and scaling these models is another crucial consideration. TensorFlow Serving is a flexible, high-performance serving system for machine learning models designed for production environments. It enables the deployment of new algorithms and experiments while maintaining the same server architecture and APIs. This capability is essential for scaling AI systems as it allows for seamless updates and integration of new models without disrupting existing services. Real-world challenges in designing scalable AI systems often include managing distributed computing environments and ensuring fault tolerance. The Lambda architecture, a data processing architecture designed to handle massive quantities of data by taking advantage of both batch and stream processing methods, addresses these challenges. The architecture comprises 3 layers: batch, speed, and serving layers, each designed to handle specific types of data processing. The Lambda architecture ensures that AI systems can process data in real time while also providing comprehensive batch processing capabilities for historical data, thus enhancing scalability and fault tolerance. Case studies provide valuable insights into the practical application of these frameworks and tools. For instance, Netflix's transition from a monolithic architecture to a microservices architecture is a prime example of designing scalable systems. By breaking down its monolithic structure into hundreds of microservices, Netflix enhanced its agility, resilience, and scalability, allowing the company to serve over 200 million subscribers worldwide efficiently. Similarly, LinkedIn's use of Apache Kafka for real-time event processing demonstrates how scalable data management solutions can improve system performance and user experience. Statistics further illustrate the importance of scalability in AI systems. According to a report by the International Data Corporation, the the global datasphere will grow from 33 zettabytes in 2018 to 175 zettabytes by 2025, highlighting the need for scalable data processing solutions. This exponential growth underscores the necessity for AI systems that can scale efficiently to process and analyze vast amounts of data. Security and compliance are also integral to designing scalable AI systems. As systems scale, ensuring data integrity, confidentiality, and compliance with regulations becomes increasingly complex. Implementing robust security frameworks such as OAuth for secure authorization and encryption protocols for data protection is essential. Additionally, compliance with standards like the General Data Protection Regulation is critical for systems handling personal data on a large scale. In conclusion, designing scalable AI systems involves a multifaceted approach that combines architectural frameworks, practical tools, and strategic insights. By leveraging microservices architecture, containerization tools like Docker and Kubernetes, and efficient data processing platforms such as Apache Kafka and Spark, professionals can build AI systems capable of scaling to meet growing demands. Real-world examples, such as Netflix and LinkedIn, offer valuable lessons in implementing these strategies effectively. As the volume of data continues to increase, the ability to design and manage scalable AI systems will be a crucial skill for professionals in the AI field. Through a comprehensive understanding of these principles and tools, professionals can enhance their proficiency in designing AI systems that are not only scalable, but also resilient and efficient.